Okay, so let me share my screen. Where is join? Oh, okay.
Recording in progress.
Okay, so let me share my screen. Can everyone see my screen? Probably.
Yes, sir.
Okay, let's start. ওকে সো আজকে আমরা যেটা দেখবো সেটা হচ্ছে এক্সকিউজ মি ওয়েল আমাদের গোল হচ্ছে quantum espresso, right? In quantum espresso you can calculate bands for phonons and you can also calculate bands for calculate electronic bands. You can also calculate something called density of state. So আমরা লাস্ট দিন যে দেখেছিলাম সেটা হচ্ছে like water bands, basically a simple harmonic oscillator example. So আজকে I think আমরা এটা ট্রাই করি phonon bands, তার like basic theory plus a simple Python code to compute phonon bands, like মানে খুবই সিম্পল সিস্টেমের জন্য। তারপরে দেখবো যে এটার জেনারেলাইজেশনটা কেমন হতে পারে, মানে এটা কাইন্ড অফ সিম্পল, সো এটা like I don't know 100 lines Python code should be enough. ইলেকট্রনিক ব্যান্ডস এটা আমরা হয়তো নেক্সট সেশনে দেখব। দিস ইজ টুডে, এটা হচ্ছে নেক্সট, এন্ড দিস ইজ অলসো নেক্সট ইন নেক্সট সেশন। তারপরে আমরা ফুললি হয়তো কোয়ান্টাম এক্সপ্রেসতে মুভ করব। সো 2 more weeks then we fully dive into quantum espresso. আর তার আগে আমাদের সবারই কোয়ান্টাম এক্সপ্রেসো একটা মানে সেট আপ রেডি থাকতে হবে, রাইট? বিকজ উই ওয়ান্ট টু টেস্ট থিংস ওয়ান থিং এট এ টাইম। প্রথমে সিম্পল মানে কোয়ান্টাম এক্সপ্রেসো সিম্পল ব্যান্ড ক্যালকুলেশন করব সিম্পল ল্যাটিসের জন্য, সিম্পল স্ট্রাকচার। তারপর আস্তে আস্তে কমপ্লিকেটেড স্ট্রাকচার যাবে, উইল ট্রাই টু গেট মোর অ্যান্ড মোর অ্যাকুরেট ব্যান্ড ক্যালকুলেশনস। আর একসময় হয়তো আমরা আমার সার্ভারটা ইউজ করব, যেখানে you know when you have complex structure and you want really accurate calculations, it can take really long time, like a lot of memory. So ওই জন্য সার্ভারটা হয়তো ইউজফুল হবে, and we'll need to use SSH for that. uh, I think গত ক্লাসে আমি বলেছি। So let's start with phonon today. So to start, so আজকে যা করব মোস্টলি ক্লাসিক্যাল। নেক্সট ক্লাসে হয়তো কিছুটা কোয়ান্টাম থাকবে, বাট খুবই বেসিক। এক্সকিউজ মি, কোয়ান্টাম নেক্সট ক্লাসে হয়তো থাকবে বাট বেসিক, জাস্ট ওই বেসিক ক্রিয়েশন অ্যানাহিলেশন অপারেটর থিংস লাইক দ্যাট, ক্লাসিক্যাল অসিলেটর। So let's start. One mass, one spring. সিস্টেমটা কেমন? You just have a mass, small m, and a spring attached to it. And this is like the wall. So what's the equation of motion? Sometimes called EOM. Equation of motion is force equals minus kx, the Hooke's law, right? Hooke's law. So x is the um, distance from equilibrium, distance of m from its equilibrium position. K is the spring constant, and F is the force, restoring force. Okay, so we can write this equation um, in a general form, which is, if we have a mass spring system, we know their kinetic and potential energy. So EK, kinetic energy, would be half mv squared, or p squared over twice m, and the potential energy, let's say this is just, okay, EK is fine. Potential energy would be, say, V equals half kx squared. And the general form um, of this force is force equals negative gradient of the potential energy. Force equals of potential energy. সবাই কি পরিচিত এই এক্সপ্রেশনের সাথে, like how this nabla or del works?
Yes, sir. Yes.
Okay. Okay, so it's a vector operator, so let me put vector sign. But আমরা যে মানে although it's a vector, but our system will be one dimensional, so it just this del is basically del x in our case, and just along x-axis for 1D. Okay, so that's for one spring. We can also write this equation of motion in a little bit different way, like this. Force is also the rate of change of momentum. Rate of change of momentum. This is the Newton's law, right? Rate of change of momentum is the force. And if we write mv there, we can write it like this: m ddt of r, or say x, because v, velocity, is bx over dt. So we get m d squared over dt squared x. That means m d squared x over dt squared is equal to minus kx, right? That's our equation of motion. Another way to write this is m x double dot equals minus kx. So this dot symbol notation is like this. So if you have du over dt, and u is a function of t, then you can write it like this: u dot, like single derivative. And if you take second derivative of u of t, then you can write it like that, like this: u double dot. Okay, this is just a notation to make it look simpler. Any questions? Okay, sometimes এইভাবে লেখা হয় অনেক সময় 1 t 2 t. I mean, it depends, like use case এর উপর ভিত্তি করে, but actual expression হচ্ছে this left hand side, right? These expressions. like actual correct mathematical expression, আর বাকিগুলো is just notational convenience. Okay, so this is for a single mass and a spin. So the next thing is that was one. Number two is um, a chain, 1D chain of mass and spring. So this system is like this. You have a mass and you have a spring. You have another mass and the spring. So springটা এরকম কার্লি না করে আমি I can do it like this to make it like easier to draw. M. All of them have mass M, and this is the spring constant K. Okay. Instead of one, you have infinite number of them. Mass spring that discharge. I think গত ক্লাসে বলেছিলাম from here you get the phonon bands for something called band. You can get it from here, like the simplest case. So question is, how do we write equation of motion for this one? Okay, so when you have a complicated system, you always want to try a simpler version of it, right? একটা mass spring try করেছি, let's try two mass and a spring, then we'll move to infinite amount, like number of masses and springs. So let's call it number three. So number two would be two mass and a spring. So we just need to write down the equation of motion. Okay, so what is the potential energy? Potential energy for this is say x1, this is x2. Their displacement from equilibrium is x1 and x2. From equilibrium for x1 particle for first particle. For x2 is for second particle. So the potential energy would be half k x1 squared plus half k x2 squared. Okay, and what will be the equation of motion? Small mass x1 double dot for the first particle would be equal to gradient of this, so minus k x1, simple. For the second particle, x2 double dot minus k x2. That's the equation of motion. But what if we consider some interaction between them? Meaning এখানে তো দুইটা particle connected আছে, right? So this is not the only potential. Rather, this is the potential due to just their initial position. কিন্তু we need to include the interaction. So vi and interaction kind of approximation হচ্ছে is like this, that the interaction depends on their relative displacement. So x1 minus x2 whole squared. That's the interaction. That's interaction potential. Okay. So এটা যদি interaction potential হয় তাহলে equation of motionটা কি হবে? Well, we know that force is equal to negative gradient of potential. So force on x1 or mx1 double dot would be negative gradient with respect to x1 of the whole potential, meaning v equals v naught plus v in interaction term. So that will be minus kx1. Kx1 comes from v naught this part, and from the other expression, this v interaction, what do we get? We need to take derivative with respect to x1. So minus k x1 minus x2. Does it make sense?
Yes, sir.
Okay.
Yes,
If you
it
have a
does.
question, you must always ask. Let me keep the chat open. Okay, for second particle, m x2 would be minus k x2 minus k x2 minus x1, right? That's the equation of motion. Including interaction. No interaction. Or without with interaction. Okay, so we have the equation of motion for like two mass and one spin. So we'll follow the same recipe for infinite chain of particles. We need to write down the potential energy, right? Because force is just negative gradient of potential energy. And we want to use this formula. So আমরা কি করব? Just potential energy টার্মগুলি আমাকে লিখতে হবে somehow. Kinetic energy is kind of simple. Okay, so potential energy would be that V0 half k x j squared, and there's a sum over all the j's. Doesn't make sense. We're just adding up all the potential energy. And the interaction term would be half k a sum xj minus xk. Jk means nearest neighbor interaction. Okay. And the kinetic energy would be, let's say, T half p squared over twice m, right? So 1 over twice m or half mv squared is fine. Half m.
Sir, I have a question.
Yes, question?
I think we need to eliminate a term from the interaction potential energy. So for xj and xk, the values of j and k would be the same. It means the same particle, but the same mass is interacting with itself. So isn't there any need of eliminating that?
Well, you see this symbol, square bracket, angle bracket here, it means nearest neighbor interaction, meaning j and k cannot be equal, and যদি লেবেল করি সবগুলোকে ইন্টিজার দিয়ে লেবেল করি, if j is 1, then k can be 0 or 2. It cannot be 3.
Thank you, sir.
Does it make sense?
Understood.
Yeah, I mean,
Yes,
that's
sir.
the notation. But your question was good. It is important. I mean, say if I write a note of this, like typed note, তাহলে ওখানে mention করতে হবে. If I say publish a paper, we have to mention this. And so that was a good question. Okay, so we have the potential energy. I guess we can try to write down the equation of motion. Let me just copy it from here. And start over there. Okay. So how do we write the equation of motion? Idea is simple. For first particle or one of the particle xj double dot, we just do this del xj of v, and V is the total potential energy, V naught plus V int. Okay, so for V naught, we'll just get one term. So let's call it K or L. I want to use unique symbols. So del del XL. So when here only one term will contribute. J could be 1, 2, 3, 4, 5. When J is L, then we'll get something out of that term. That will be minus K XL, negative minus sign, and that's from here. And for the second term, we need to kind of expand the term a little bit. So half K. So JK, it means nearest neighbor. All right. So it can be xj minus xj plus 1 whole squared, right? J, when I mean, if k is j plus 1, then it can also be xj minus 1, then second term would be xj whole square. So, and the plus term, I think, let me move this downward a little bit so that I can fit this here. Sum over j only. Does make sense? Idea is j can be if first index is j, then k would be j plus 1, right? That's the first term. Nearest neighbor interaction. Now, if k is j, then the first index would be j minus 1, the previous one. Idea is, so here I have j minus 1, j plus 1, and j plus 2. So we consider interaction between j and j plus 1. That's this term. And we can also consider interaction between j and j minus 1. That's the second term. Does it make sense? J appears twice. Let me write it like this. This symbol and this symbol. Okay. Just symbolically, j appears twice, and that's kind of important. Okay, and when we take partial of this interaction term, what do we get? We get k. For the first term, we get xj minus xj plus 1. And from the second term, we get xj minus 1 minus xj. So now, does it make sense? Do we have any questions? Because if we take partial derivative, this is what we get, right? Because there's a square, right? Or do we have a minus sign somewhere? Or is this fine? No?
This seems fine.
seems fine, but I think xj, we have a minus sign actually here, because you see the order, we're taking derivative with respect to j, right? And there's a minus sign right here. So when we do this, del x of xj minus 1 minus xj whole squared, we get xj minus 1 minus xj times del xj of minus xj, right? So this minus, there's a minus sign in front. Okay, so ultimately we get minus k xl minus k twice xj minus xj plus 1 minus xj minus 1. It, like this 2 is important actually. mxl double dot, oh, this should be l. L plus 1, L minus 1. Uh, okay, that's the equation of motion. Okay, for one-dimensional mass spring system, and we're almost done. So what do we do now? How do we get the expression for frequency? So you know the dispersion curves or bands are energy as a function of wave vector versus k graph, or sometimes frequency versus k. Because if you know frequency, you can calculate energy. In quantum mechanics, it's h bar omega. In classical, it's proportional to omega with a factor. So one of these, we need to get one of these, like energy as a function of k or frequency as a function of k. And to do that, we need to apply Fourier transform. So have you guys seen Fourier transformation before in any course?
Yes, sir.
Okay, good.
Yes.
Long ago, I have
Okay,
forgotten.
so idea is really simple. So you have a function of x, and if you multiply this function with something like this, ikx. Now, why is it, e to the power minus ikx? That's the details. But let's just consider this. You're just multiplying it by a weight factor and doing an integration, then that will be a function of k, because when you integrate out a variable, it's called, we have everything as a function of x. We are integrating out that variable x. What we are left with is k. So on the left-hand side, it will be a function of k. And inverse Fourier transform is f of k e to the power plus ikx and dk. This is inverse transform. Okay, so idea is really simple. You have a function and you multiply it by some weight factor, and you get a different function. What it does, its properties, it basically picks out the frequencies. I think it would be easier if I later on show this in program in Python, that you can pick out frequencies from from one curve by applying Fourier transformation to it. yes, like details in Fourier transformation. So, but for our case, it's kind of enough that you understand the idea is just multiplying by e to the power minus ikx and doing an integration to find something as a function of k. Okay, there is like properties of Fourier transformation. That's that's like a, I don't know, 2 3 weeks course on itself. And some we normalize these transformation by a factor square root of twice pi on both of them. This is called a normalization factor. Yeah. So let's apply Fourier transformation here. How do we do that? Let me copy this equation. Now we want to approximate the solution. In the form like this: xl equals u e to the power I k um, al minus omega t. Okay, so what are these? So this L index is the L index over there, and A is the separation between the masses and springs. So this distance is A. Separation between mass is A. Okay, so we just multiply all the terms here in the equation of motion. I'm sorry, we just replace all the xl in the equation of motion by this expression. So what happens if we do, if we take a single derivative of xl, we get u. U is just a constant. So we get here e to the power I kal minus omega t. And since we're, this dot means dxl over dt, we'll get minus I omega as a factor. And if we take partial derivative twice, we'll get I omega whole squared. And here we'll have u e to the power I kal minus omega t, or minus omega squared u minus omega squared xl. Does it make sense?
Yes, sir.
Okay.
Yes.
Okay, now we just plug this in there. So the left-hand side would be, let me use color. That part would be m minus omega squared xl, just xl, yes. On the right-hand side, we'll have minus kxl, and then the rest of the part would be minus k 2 times xl minus, this is xl plus 1, right? So we'll write u e to the power I k a twice l, l plus 1 times minus omega t, minus u e to the power I k a l minus 1 minus omega t. I just use these labels instead of like plug them in here, right? Instead of L, it's L plus 1 or it's L minus 1. Okay, next line you can write it like this: M omega squared, let's say U, equals minus K U minus K twice U minus U times, you see, we have plus 1 here. So that's a factor e to the power I K A times e to the power I K A L minus I omega t. And for the second term, it's U e to the power minus I K A and another factor of this same factor. We have less space, it seems. Okay, e to the power I K A L minus I omega t. Yep, almost. I think I should write it XL, not U yet. Okay, this should be XL. Yeah. So next line you can write minus M omega squared U equals minus K U minus K twice just 2 minus e to the power I K A minus e to the power minus I K A, and here would have U. So what happens is this e to the power I K A L minus I omega t, that term gets cancelled out from all sides. Not just that, you see, U is also common, right? So we are left with this minus M omega squared equals minus K minus K times 2 minus e to the power I K A minus e to the power I K A, just this expression. And next line would be minus K 2 minus 2 cosine Ka. We have a problem. Problem is I'm mixing up the wave vector and spin constant. Let me fix it quickly. So let's call this spin constant K prime instead of K, right? Instead of K, they are K prime. All the spin constants are K prime. And for Fourier transformation, this is K, and spin constants are K prime. Okay, then it'll be minus K prime to 1 minus cosine Ka, and you have minus sign on both sides, so it would be omega squared equals K over M plus K prime over M times 2 1 minus cosine Ka. Does it make sense so far?
Yes.
Okay, good. So we have the frequency, and if we just take square root, it will be plus minus square root of this term K prime over M plus 2 K prime over M 1 minus cosine Ka. And this omega is nothing but a function of k. And if you plot this omega k as a function of k, then that's your dispersion curves, and it's nothing but 1 minus cosine ka. So what does this graph look, what does it look like? 1D phonon bands. I think this, okay, 1 minus cosine would be 2 sine squared, right? Or we can just try to plot it directly. Uh, okay. 1 minus cosine Ka is 2 sine squared Ka over 2. Is that the right formula?
Yes, that's correct.
Okay, so here we can try to simplify the expression a little bit, because you see this is just constant term, right? First k m prime. So we can write omega k approximately equal to twice k prime over m, ignoring the first term, and then writing 2 sine squared ka over 2. And square root is there, and then we'd get 4 k prime over m, square root a constant, and then sine ka over 2, right? So this is interesting. So it's just omega is just a sine curve, right? And we can try to find this period. So if k is 0, what is omega of 0? What is the maximum or minimum of this function? So maximum minimum of sine would be the maximum and minimum of omega, because this is just a constant. So sine ka over 2 is minimum value is um, no, let's, yeah, it goes from -1 to +1. So let's try to find when it becomes 0, right? Uh, okay, so we want to find it when it becomes 0. How do we find it? Ka over 2. Is it so when 0 is 0,
When k becomes 0,
n pi, right? If k over 2 is n pi, n is 0, I mean sine 0 is 0, sine pi is also 0, right? Pi over 2 is 1. So sine k over 2 is 0 when k over 2 is n pi. That means k is equal to n pi or 2n pi over a, right? And sine k over 2 is maximum or minimum, say plus minus 1, when ka over 2 is plus minus n pi over 2. Uh, is that correct? And
No, sir, it should be n plus 1 pi by 2. I think.
n, because n is an integer, right?
Yes.
Okay, n plus
And
1.
it can,
Wait a minute.
when it becomes even numbers, the pi by 2 becomes a pi, which gets the value of sine 0. I think n plus
So
1.
it should be twice n uh, plus 1, right?
Yes, sir.
Pi over 2. So k will be equal to um, pi over a, times twice m plus 1 plus minus. So, okay. So we get the maximum and minimum when it becomes plus 1 minus 1. And you see here we have the sign squared. That means if it's sign plus 1 or minus 1, omega would be the same because we're squaring the sign and the square root is there in the original formula. And here we actually take the absolute value, right? So, okay. So what are the limits? If n equals 0, k would be uh, plus pi over a or minus pi over a. Here a is the uh, lattice vector or distance between two spring, distance between two mass or lattice vector. Because in one-dimensional system, that's the only vector there, like unit vector, unit steps. And this is called the first B1 zone. So minus pi over a to pi over a. Uh, let's include this. Uh, uh, First B1 zone. This is French uh, name, so you don't pronounce the L. It's a little difficult to pronounce. I still don't know if I can pronounce it correctly, but it goes something like B1 zone. B1. Am I missing a I somewhere in the spelling? I think
Yes,
so.
sir. Before the N.
Yeah, yeah. Okay. So now we know what is the Brillouin zone. And when we plot this omega, we usually plot like this in the range minus pi over a to plus pi over a. This term is important in condensed matter because most of the times we deal with only first Brillouin zone. Sometimes for special cases we move to second Brillouin zone, meaning when n equals to 1. But most of the times, first Brillouin zone will give you everything you need. And okay, so we have the sine curve k over 2. So in here it would be 1, right? I'm trying to plot the graph. So in the boundary it will be 1. Uh, and in the middle it will be 0. So it's something like this, right? Or we know it's sine, so we can just draw a smooth curve. This is called the dispersion curve or the bands omega as a omega of k as a function of k. Any questions? Okay. One important thing to notice here is that our equation of motion was in, where is it? Initially it was here in x space or configuration space or position space. After we Fourier transform, we get in the equation of motion in momentum space or in k space. Okay. And in momentum space, it's like this. So what happens is that you see in position space, you have mass spring, infinite repetition of system, and it's periodic. And whenever you have some kind of periodicity, one idea is to just apply the Fourier transform and see if you get something, in a finite range. For example, whatever happens in the range minus pi by a to plus pi by a, whatever shape you have, that can tell you how the entire system would behave. This infinite chain, all its behavior can be captured just by studying what's happening in this range, minus pi by a to plus pi by a. And this is a very important concept. The reason so in solids, we have, instead of a single atom, we have sites or molecules, and each site is repeated in 1D or in 2D, right? It's in a periodic pattern in 3D. I don't know how to draw it here. I mean, I can try to draw, but you get the idea. It gets repeated infinite number of times, and it's really difficult to capture what's happening at each individual sites. But when you write down the equation of motion and do a Fourier transform, you get something dealable, something in a finite range. It's continuous. You see, here it was discrete, but in K space, it's continuous. In K, discrete in X space. This is K space. This is X space. Okay. So yeah, that's all the reason we do Fourier transformation, to extract something useful, dealable in a finite range, instead of dealing with all the particles. We can write equation of motion for all of them and so, like, try to find out where each particle will be, or we can just look at the curve for omega and see, okay, this is for this momentum, that should be the frequency for entire system. And then we can easily calculate, if we need to, each position of each atom. But usually we try to express the useful quantities in terms of omega k, so that we don't have to deal with individual atoms. And when you understand this Brillouin zone and this wave vector k, there are other, for example, X-ray diffraction, like how between different layers, how X-ray incoming photon gets reflected by different planes, and you generate, how this momentum transfer works. You can, like, that's all in momentum space. Okay. So this Brillouin zone and dispersion relations, the bands, they're really important. Uh, yeah. Any questions? Okay. So, but this, yes, question? Okay. So this process is useful, but we want to find a general approach so that we can write a code to compute these bands for us, right? We don't want to derive the expression for a single atomic chain or diatomic chain every time. Or like if I say I have 5 atom in a one-dimensional system, or 2D system or 3D system, we don't want to rederive this expression. We want to find some mathematical way that can be implemented in a code so that it can compute the uh, bands, dispersion curves for us automatically. And it seems there's a way, and let's try to look at that. So I think starting from monoatomic chain would be a good idea. Uh, Force constant matrix, matrix phi, and dynamical matrix, matrix D of k. these will help us to find write a general expression for the equation of motion and to find the frequencies. So the way it works is, so we have the potential, right? Potential, total potential, and this phi is nothing but so this is basically function of xi or xj and xk, right? So phi is del xj del xk, second derivative of the potential. That's phi jk. So the equation of motion would be F equals, or I think M x j double dot is equal to phi jk xk, and there's a minus sign. Does it make sense? It's a very general expression for equation of motion. Everything we had here, these terms, they would be, we have XL and some coefficients. The coefficients would be inside this phi, and the XL would be here in XK. For 1D system, phi jk is just k, uh, one mass. Okay. So one mass and spring like this. For that, phi jk is just k, and for two mass and a spring, phi jk is I think it's a matrix. If I can look at the, where is the, okay, where's the equation of motion? Okay. For two mass and a spring, it would be a matrix um, minus k and k minus k minus kk, something like this. I think there's probably a factor of 2 here. That's phi. Okay, so phi is just, if we take partial derivative, second derivative, we can get phi. And for infinite chain of mass spring system, phi is again a matrix, but since it's infinite system, it's like an infinity by infinity matrix, and we only need the important blocks of that matrix, and we can write down the block. If we write down the equation of motion, let's see. Yeah, that was the equation of motion for one-dimensional mass spring system. For simplicity, let's assume this is 0 for simplicity. Okay, and let's try to write down the phi matrix for this case. So it would be on the right hand side, we have xl minus 1, we have xl, we have xl plus 1, and I'm just writing down the phi from equation of motion instead of taking partial derivatives. So we have for xl, we have this is a minus sign here, so this is twice k. For xl minus 1, we have minus k, this term, and for xl plus 1, we have minus k. And on the left-hand side, we have m xl double dot. Does it make sense if you do the matrix multiplication? I just wrote down the one row. If you multiply, you see we get the equation of motion. Try to do the multiplication now and see if you actually get the equation of motion. Okay, you have 1 minute. It's 11:04. Sorry, 11:03 here. So 1 minute would be, I think, 9:04. Okay. Okay, so have you guys checked if it actually matches up with the equation of motion?
Yes.
Okay, so yeah, this will work. This is our phi in this case. So since we have the phi, we can do Fourier transformation of this, and you see, um, what does this term actually mean? So this is k minus k. So this term is the interaction between you know uh, xl plus 1 and xl, right? I mean, in this chain, we have l plus 1 and l minus 1. So xl and xl plus 1 এর মধ্যে যে interaction সেটা ক্যাপচার করছে এই টার্মটা, right? So this is at a, and if this is 0, this will be minus a. আমি l কে সেন্ট্রাল অ্যাটম হিসেবে চিন্তা করছি আর কি। সো যেটা মাইনাস এ, তার জন্য কোন টার্মটা কাজ করছে? দিস ইজ দ্য টার্ম, রাইট? দিস ইজ ফর minus a, this is for plus a, and this is for 0. It's just a notation. It means is it the left atom or right atom or the central atom? এর একটা label আছে. This label is like this: r equals minus a, 0, or plus a. So we write the phi as phi 0 equals twice k, phi a equals minus k, phi minus a equals plus k. It's just a notation. মানে central atom or left one or right one. Minus k. Okay. This notation is also kind of important because when you write down the code, you need to have consistent notation, right? 0, a, minus a. So now we can apply Fourier transformation here because d of k would be phi 0 e to the power I k a times 0, I k 0, for example, plus phi 1 or phi a e to the power I k a phi minus a e to the power minus I k a. Okay, and this is twice k, e to the power 0 is 1, plus phi a is minus k, e to the power ik. This is k prime, spring constant. Now let's mess this up. So, right, k prime. Yeah, so since I probably messed up this prime, k prime and k, one homework would be to check the note, like I'll post this PDF and try to find if I missed something somewhere and if it makes sense, right? কোনটা কে হবে, কোনটা কে প্রাইম হবে, এটা তোমাদের খুঁজে বের করতে হবে. That's the homework. And last one is k prime to the power I k a. And then we'd get 2k prime, 1 2 minus e to the power I k a minus e to the power I k a minus sine k prime 2 minus 2 cosine ka k prime uh, 2k prime, and this would be 1 minus cosine twice a, so 2 sine squared k a over 2. So this term is exactly the same as the previous term, and here in this dk matrix we can mass normalize the phi. So mass normalized phi is just, in the simple case is let's divide by mass, right? Then we get mass normalized phi. That means uh, instead of m here, we divide by m here. And this is like over m. And here, and this is the exact expression, uh, almost. So you see, this was the equation of motion, right? The general expression. And after do Fourier transformation of this equation in X space, and if you do Fourier transformation of this equation, you get omega squared equals d of k times I think just omega squared. Let me check the formula. Yeah, it's just omega squared. Because you divide. Okay, let me rewrite this. Xj double dot equals minus phi tilde. This is mass normalized xk. And if you do Fourier transformation ft, then you get omega squared equals d of k, right? And this is the equation of motion in k space, meaning if you take square root of d of k, you get the frequency. Okay, for simple case. For complex case, it will be the eigenvalues of d of k. So the frequency of k would be square root of that expression, 4k prime over m sine squared ka over 2. Any questions? এখানে একটু question থাকতে পারে, which is normal. So I'll share this PDF. So তোমাদের কাজ হবে একটু স্টেপগুলি ভেরিফাই করা, is it correct or not. Now আজকে how to write the phi matrix for 2D system. I mean, sorry, for a system of 2 atoms. এটা দেখি, then probably would conclude today's session. Okay. diatomic chain. So we have mass, square, circle, square, circle in that sequence. And here we'd call this a cell, a unit cell. And for circles, the mass, let's say this is capital M, this is small m. Okay, so it goes in alternating patterns, and the spring constant for all of them is K for simplicity, or K prime. We can have a system where spring constants can be different between small and big M, like between inside a single cell and outside. So it could be K prime and K double prime, but let's not go there. This is a simplest system, and we want to write the equation of motion. Question is, how do we label these squares and circles? One easy way is to use even and odd terms. So this is x twice n, x twice n plus 1, x twice n plus 2, x twice n minus 1, right? So all the even particles are big M, all the odd particles are small m, mass. We can try to write down the equation of motion. Let's look at the previous equation of motion, and we can compare um for 1D chain. Okay, and let me make it small as a reference. Like this is our reference. We're going to look at the equation and try to write down the equation of motion for diatomic system. আমরা potential expression লিখে কিন্তু করতে পারি, but just to skip few steps. So আরেকটা homework হবে তোমাদের জন্য যে এর potential energy লেখার চেষ্টা করবে expression, then you just take partial derivative to find the equation of motion. আমি হোমওয়ার্ক গুলি এই পিডিএফ এর শেষে লিখে পোস্ট করব গত দিনের মতো। দেখো, হোমওয়ার্ক কিন্তু তোমরা ট্রাই করবা, প্রবলেম হলে কোয়েশ্চেন করবা। আর since this is like a different type of course, এখানে grading is basically, are you I think next time থেকে are you attentive? Okay, so grading is a little different. Okay, so equation of motion would be m. Okay, let's say for big M, x twice n double dot would be equal to, so we can simplify the expression by saying this is 0 minus k prime 2x twice n minus x twice n plus 1 minus x twice n minus 1. Does it make sense? Like match করে লিখছি small m.
Yes, understandable.
Okay, good. Twice n plus 1 would be minus k prime 2x twice n plus 1 minus x twice n minus x twice n plus 2. So এখন যদি লেবেল গুলি আমি দিয়ে দেই, it will be easier, I think. So we have we already have the labels. Style should be this color. So what's happening when you have twice n plus 1, this one, the next particle and previous particle, they are in the equation of motion, right? So this one, next, previous one, and next one. Okay. So that's our equation of motion. এখানে কিন্তু why do we need to write them separately? Because we have two different mass. That's why we need to write them separately. And let's try to figure out the phi matrix. And the phi would be, uh, we can try to write down this x twice n, x twice n plus 1, big M, small m, d squared over dt squared, something big here, uh, and here it will be uh, twice n minus 1, twice n, twice n plus 2, twice n plus 1, twice n plus 2, right? We only have these four expressions. Okay, now we can try to write down the equation. So for x twice n, is for twice n is 2k prime. This term twice n plus 1 is the next one, so it's minus k prime. This is 0, this is minus k prime. We have 4 elements. For next one is 0 minus k prime, twice k minus k prime, then twice k prime minus k prime, 0 0, 0 0 minus k prime, twice k prime. And I can write it m x twice n minus 1, capital M x twice n plus 1. So if you see the pattern, you can you know, write down other terms as well. So this is our phi ij. This is just x j, and this is xi with mi double dot. Question?
In the left column matrix, the last entry, shouldn't it be twice n plus 2?
Plus 2, yes, yes. Thank you. Okay. So how do we get the phi ij? So remember, phi 0 is for self-interaction, right? That means if we consider this as a block, for this block, twice n and twice n plus 1. And here it will be like x, not just that block is this block, right? So which part of the matrix is responsible for these two blocks, the relationship between them? Is this part, right? So that's our phi 0. Twice k prime minus k prime minus k prime twice k prime. And what is phi a? The next part is, I think, okay. Is there any mistake somewhere? That part. No, there's no mistake. And if we want to see what's happening with the next cell, then I think it's better to choose this part, the this cell with the next cell, right? Twice n minus 1, twice n with twice n plus 1 and twice n plus 2. So that will be this cell. So it's like a block matrix, right? you take the first block here and last block there, and that's connected to this block right here. Are you familiar with this block matrix terminology? Like you can divide a matrix into different blocks and operate in each block individually. Okay, so let me write down phi A. It will be 0, 0 minus k 0, k prime, and phi minus A would be 0, 0, 0 minus k prime. Okay, so we have the phi matrices, and now we can do Fourier transformation. Remember, d of k was phi of 0 e to the power I k 0, or just phi of 0, phi of a e to the power I k a, phi of minus a e to the power minus I k a. These are mass normalized, but for now I'm just writing the k term, and phi of 0 would be twice k prime minus k prime minus k prime twice k prime. This term would be 0, 0 minus k prime 0 e to the power I k a. Next term would be 0, 0, 0 minus k. I think this should be k prime 0, 0. And I know it's kind of getting a little bit complicated, but we're almost there. IKA minus sign. And if you add up all the numbers together, you see we get twice k prime minus k prime 1 minus e to the power minus IKA. Here we get minus k prime 1 plus e to the power IKA, and here we get twice k prime. Just adding up all the terms. And this is the matrix. If you remember, omega squared is equal to d of k, right? That was the equation of motion in k space. And since omega is just a number, but d of k is a matrix in this case, we would say determinant, or let's not complicate things. Eigenvalues of d of k would give me the frequencies. Okay. So how does it work? So d of k is a 2 by 2 matrix. 2 by 2 matrix. That means it will have two eigenvalues. That will give us omega 1 of k and omega 2 of k. Okay. And if you solve it, you'll see you can, draw this omega as a function of k. Okay, and you see we get two bands in the Brillouin zone. One looks like this, another one looks like this. This is called the optical, and it's called acoustic. Okay. So for diatomic system, we get two bands, optical and acoustic. So these are, d of k is not mass normalized in this case, but I think you get the idea. 2 by 2 matrix for diatomic system, we get two frequencies. Does it somewhat make sense? You need to review this. I think I have a kind of better note written in LaTeX. Um, I'm probably gonna share that. That way it will make more sense, I think. But do you get the idea that if you have more atoms, you're gonna get more bands? And this is like a general way of solving it. Uh, any questions? Okay. Okay, so let's take a look at one of the code snippet that I have. Uh, I think this is the
Sir,
yes.
before you move on to the code, so in the last picture, the two bands are saying one optical and the other is, sorry,
Yes,
sorry,
one optical, one acoustic.
acoustic. Is there any reason for that? Like,
Is
with phonon would be always acoustic. That was my understanding.
well, these are just names, and yes, there's a reason for that. And the reason is, see, if you notice here, the optical branch is always at high frequency, right? Meaning energy is always high. It's never zero. Omega k is never zero. It's always greater than zero, like really high, right? For acoustic branch, the frequency could be as low as zero. That's one of the case. And when you have instead of two atomic chain, you have three atomic, four atomic chain, you always have one acoustic branch, I think. And so for n atomic system, you have one acoustic and n minus one optical, meaning all the other bands will have higher, you know, higher energy. And it's just a, I think, uh, the way they write the naming. And another reason is how they interact with phonons and photons. Okay, for now it's just their name, but it's I think they're named because how they interact. Okay, so if you solve this system, find the what do you call their normal vectors, like normal coordinates, then you can find how they oscillate, like each atom. You can write Python code and find the frequency of acoustic and optical branch and see how they oscillate. If you use acoustic, uh, you know, frequency, then you see, all the phonons will be in phase, all the particles will be in phase with each other. Okay, so all of them are, say, moving to the right at the same time or left. But with with optical mode, they will be out of phase, meaning, so if you consider each cell, uh, in each cell, two atoms, if they're moving like this, both to the right or both to the left, then they are acoustic, they're in phase, and out of phase would be, I think that's inside the cell. So uh, in phase would look like this. Both are moving to the right, square and circle, right? Or both are moving to the left. And in out of phase case, this is acoustic, this is optical. And out of phase would be both of them are moving away from each other or toward each other. Okay, so it's in normal coordinate you'd see this. And what is the normal coordinate? Now things would get you need little more details to see these, like how they're moving in phase and out of phase. But we can get into details, but that's why they have like in phase and out of phase case, acoustic and optical branch. And I think the name is how they interact. Okay.
Yeah, I got a bit of an idea.
Okay.
But another question,
Yes.
like I followed along your calculations. I understood most of it, but I kind of lost the big picture. Could you just briefly recap it? Like,
Okay. Yeah, good question. So yeah, big picture is always important. So big picture is, if you remember the general equation of motion, is basically your mass x I, the particle, is equal to minus phi ij xj. And if you can find phi ij, you can do a Fourier transformation and you get mi omega squared d of k. And when you do Fourier transformation, you get a minus sign on both sides, so the minus sign cancel out. And this is in x space, this is in k space, and d of k is a matrix. So if you find determinant of omega squared, the identity matrix minus d of k, that the condition is the determinant must be 0, and because of that condition, the eigenvalues of d of k would give you all the modes. Gives all the modes. Okay, and this works because we have the potential, and the potential can be written like this: V naught plus x I del V over del xi. If Fourier expansion of the potential xi xj del del square V del xi del xj, and all the higher order terms, we consider all the higher order terms to be negligible. And this is called the harmonic approximation. And in harmonic approximation, this del V over del xi, this becomes 0. Okay, and you will only have this term. And when you have that, this is basically our phi ij, right? And for that case, we can always write equation of motion like this for small oscillation. Okay, harmonic approximation and small oscillation, we can always write express equation like this, and then Fourier transformation becomes something like this, and the eigenvalues of d of k would give us different modes. For monoatomic system, diatomic, triatomic, any number of atoms in 1D chain, or in 2D or 2D system, 2D or 3D chain. Okay, this like in this approximation, we can calculate bands for 1D, 2D, or 3D system if we can just find phi ij and then do the Fourier transformation to find d of k. Does it make sense somewhat? Like that's why I have introduced the concept of phi and d of k.
Yeah, the last brief was very helpful.
Okay, okay.
And
Yeah, so
yeah,
after this we want to generalize, right?
I have one last question.
Yes.
Uh, so today we're studying phonon bands. Previously, we have talked a bit about electronic bands. In my understanding, electronic band essentially means in a quantum system, such as harmonic oscillator system, electrons cannot just stay anywhere. They have to stay at specific energy levels, or maybe the level can pile up and make a band. So that's where the electronic bands come up. Basically, we're talking about energy bands. In phonon bands, are we also talking about energy bands here? Could you show me the physical implication of it?
Okay. So, from your question, I get that we write the Hamiltonian, right? For, electrons or phonons, we write the Hamiltonian in X space. So, for phonons, it would be half m omega m v or x dot squared plus half kx squared. For even for electron, we can model system like this, but the potential will be replaced by Coulomb potential or other, approximate potential in different cases. So what we do Fourier transformation on this k of x because we have a sum there, right? Not one atom, but a lot of them. Then we get something h of k, and then h of k would be dk small h of k. And this expression for small h of k would be, uh, half. Instead of mass, we'd have something like this. Instead of x, um, you have something, a function of, let's say x tilde, function of k squared plus half. I think this is omega. Okay. This is like that. And then you have omega of k, and then x tilde of k squared. So when you do Fourier transformation on the Hamiltonian, the expression looks like this. Um, you know, this is the Hamiltonian in K space for continuous system for one-dimensional monoatomic chain. We can find the expression for Hamiltonian in for diatomic case and for any number of atomic case, and even for electronic system. If we assume this harmonic approximation, the Hamiltonian may look like this. I mean, it will always be a function of k momentum. Okay, so those bands for individual atoms, the electronic states, they're in X space. For combined system, the entire system, it would be in K space, in momentum space. Okay, then we don't talk about individual atom at all. We just want to know their momentum, and that would be applicable for the entire system. Okay, and we have talked about electronic bands a little bit, but I think in next session we'd solve, um, you know, probably will look into one of the model. I think there are many models, the Cronin-Penney model, the tight binding model, and few others. But I'll try to pick a simple one that's easy to understand, and maybe you can write some code and see how it works. And then we'd move to the method that's used in quantum espresso. I think that's called Kohn, Sham, Hamiltonian. They're like different terms, and you do iterative calculations to find the bands. So yeah, your question is, um, instead of individual atom, we express the Hamiltonian from x as a function of x to as a function of k, right? And then that kind of gives us the picture in K-space. Then we no longer talk about individual atom, rather what's the momentum, and we get energy for the momentum. That's the band. Does it somewhat answer your question?
Yeah, I got a bit of it, but then is it like viewing the same thing from different lenses? Like if we're doing Fourier transform, we are essentially not changing the physical system, right?
No, we're just looking from a different from a transformed coordinate system. So Fourier transformation is just a transformation. So instead of looking at the system in X space, we look at the system in K space.
Sir, I have a question. Is it like we're looking at from the reciprocal lattice of what you said?
Reciprocal lattice, exactly. K-space lattice is reciprocal lattice. So the 14 types of Davis lattice, they're in K-space, right? Like you write the unit cell in X space and you may do a transformation and then get the Davis lattice. So if we want to talk about that, so simply we have lattice vectors in 3D A1, A2, and A3, right? And they have X, Y, and Z components. Uh, plus, what am I doing? Right? For all of them, A1, A2, and A3, in configuration space, in the reciprocal space, it would be B1, and the way B1 is defined is A2 cross A3 divided by the volume, which is A1 cross A2 dot A3. And I think there's a 2 pi factor here, right? So B1, similarly, you would get B2 and B3 vectors. Those will be the reciprocal lattice vectors. So we talk about what happens in reciprocal space. Okay. And if you check the dimension of this the dimension of A would be in Armstrong, or let's say in meters, well, Armstrong, and dimension of B would be in inverse Armstrong, 1/Armstrong. So that's basically a dimension of the momentum K. Okay. So it's like a lot of details. And as we move along, we'll try to, whenever one thing is kind of relevant, we'll probably focus on that. But yeah, I think you can try to read a standard condensed matter book, say by Kittel, and try to read about these lattice vectors and reciprocal lattice vectors. So that's in momentum space. Kittel book. Okay, does it somewhat answer your question?
Yeah, it is helpful. I have to study a bit.
Yeah, um, I think that could be one of the readings that you all can do, that read those chapters in Kittel book, right? Yeah. Okay.
Yes.
Any other questions? Okay. So now let's just take a look at the uh, code that I have, and your task would be to write similar code. Stop share. I think I can exit from my iPad. Leave. leave meeting. And do I have the code here? Yep. So let me share my screen and just show you the code. I wanted to do some live coding, but it's already almost like 2 hours. So I'm just going to show the code. So I have, to build one-dimensional D matrix and do the Fourier transformation. Here I'm doing the Fourier transformation. Can you see the screen?
Yes.
Yes, sir, we can see this.
And then we find the eigenvalue. And then we find the frequencies appended, then plotted using matplotlib. So for this, we need NumPy and matplotlib. And to run the code, you can just do Python phonon.py. So the bands, they look like this. The top one, orange one, is the phonon band. The bottom one is the acoustic band. We can change the label, but this is how it somewhat looks like. And there are approximation that the force constant is 1, mass of the first particle is 1, mass of the second is 2. So those are like used as a constant. And why do we take the square root? Those things are, I'm going to share a PDF, and it will contain some details, like how we mass normalize the blocks and D matrix. Okay, but this is what it kind of looks like. And in this code, if we change the block, this, this is basically phi 0, phi 1, phi a, and phi minus a, at 0, +1, and -1, then it will calculate more bands for, say, 3-atomic system in 1D chain. But you probably wouldn't have to change anything here. You change each block, and that would do the computation for you. I guess I can share this code as well. And yeah, so let's do this. So all of you are familiar with like Python, right? How to write code and how to plot and everything. If you don't know, we can go over things a little bit. But are you guys familiar with Python? Like, can you? So this is like a 70-line code.
Yeah, I'm somewhat familiar.
I'm familiar with it.
Okay. Okay. We yeah, try to run this code, and if you encounter any problem, we can review it. So we can sometimes maybe spend a session just to do a question answer session and review code, right? Write things step by step and review it. But yeah, that probably would be a good thing. And yeah, I can share this code. Okay, any more questions today? I think one of you had a problem with VirtualBox installation. We can look into that. But if anyone else have any questions, please ask. Okay. Um, okay. Okay, so I guess that'll be all for today. So your homeworks would be to kind of review the steps that I have done, find if there is a mismatch in K and K prime, and I'm gonna post the code and little bit rigorous expressions, probably in a PDF, LaTeX PDF format, and hopefully and you should try to run the code for 3 atomic system. Try to find the phi matrix, the force constant matrix, do the Fourier transformation for a system with 3 atoms in a chain. Okay, that's the homework. Okay, so I guess that's it. I'll see you guys next week. And yeah, any more questions?
No, sir. Thank you.
Okay, welcome. Okay, see you guys next week. Take care.
Thank you, sir. Assalamu alaikum.
Walaikum assalam.